Okay, we're going to finish up our work on rotational dynamics by talking a little bit about gears and gearing. And this is something that it's come up like once or twice on the homework. I just think it's kind of an interesting topic, and if you take engineering courses, you might be able to get more into this. But it does come up once or twice on the homework, so I wanted to cover it just for the sake of you guys knowing what to do there. So let me show you the example that I have. Let's say that you have two discs, and these two discs have a chain looped about them. So that it doesn't slip or slide. And for the sake of what we're doing, let's say the discs have the same mass. Okay, so a picture might look like this. I've got one disk of radius r. I've got one disk of radius, it's probably not quite accurate, 2r. And there is a chain or a belt that goes around both of these that connects them. Okay, it's a continuous belt just like this. So that as one rotates, it moves the chain or belt, and the other one also does. First thing I want to talk about is comparing the moments of inertia. The general formula for moment of inertia for a disk is as follows: 1/2 mr squared, where m is the mass and r is the radius of the disk. So for the smaller disk, we would just have 1/2 m, same mass, we'll just call it m, r squared. But for the larger disk, would the moment of inertia be twice as big, 4 times as big, 9 times as big, 8 times as big? What would it be? Well, it would also be 1/2 m, but the radius there is 2r squared. When we square 2r, we get 4r squared times 1/2 m. That gives us, let's see, 2mr squared. Now, how big is that compared to the smaller moment of inertia? You might be tempted to say it's twice as big, but look at the coefficients. Is 2 twice as big as 1/2? No, it is 4 times as big. So we would say that I2R equals 4IR. Okay? So just make sure that you're clear on the algebra there. What I really want to talk about is how the both linear and angular speeds of the disk's rotation relate to each other at the outer edges. Okay? If this chain or belt or whatever you want to call it, if that has to stay on the disks, then what that means is we said that it doesn't slip or slide. So that means that every point on the belt, there's no shifting. It moves smoothly over these two disks. There is no jumping. There is no like holding back and slipping forward. What that means is every point on the belt has to be moving at the same linear speed. If it wasn't, let's say if this part of the belt was moving faster than this part of the belt, then there would be stretching. If this part of the belt was moving faster than this part of the belt, there'd be a bunching up, and we don't get that, okay? That doesn't happen. So the linear speed, v, of the chain must be equal at every point. Otherwise, you would have these slips or slides that we said don't happen. Okay, we're saying they don't happen. So what that means is every point on the belt is moving at the chain is moving at the same speed. That means that here the chain is moving at the same speed as it is here, and that would be the linear speed. Okay, it's moving over the same amount of distance in the same amount of time. So we could say that for the outer edges of these two disks, VR equals V2R. The linear speeds are the same. Now, what about the angular speeds? Are those the same? Well, we know that V equals R times omega. That's the conversion between linear speed and angular speed. So we could say that R times omega sub R equals 2R times omega sub 2R. Okay, the radius of the first times the angular speed of the first equals the radius of the second, which is 2r times the angular speed of the second. I have an r on both sides, I can cancel those out, and what I'm left with is this. The angular speed of the bigger disk is half that of the smaller disk. And that kind of makes sense, doesn't it? If each of these points, if all points on the chain are moving at the same speed, then if this is moving as fast as this is going to turn a lot quicker because it's a smaller disk. This is not going to turn, it doesn't need to turn as fast in order to move at the same rate. So the angular speed of the bigger one is slower, the angular speed of the smaller one is faster. Okay, and the relationship is expressed right here. And you actually get the same result for the acceleration, in that the angular acceleration, if there is any, of the first, or the angular acceleration of the bigger disk is half that of the angular acceleration of the smaller disk. Okay, so that's just kind of an interesting thing, and we're not really going to study that all that much. I just kind of wanted to point this out because it does show up on a homework problem. We won't go too in depth on that, but if you were to go study, like let's say probably mechanical engineering or some sort of engineering, you might look a lot more at gearing, and it's actually a pretty interesting topic that I know very little about. Okay, but it is kind of interesting, and there are lots of applications of this. So what we've done so far is we've looked at torque and rotational dynamics. We've taken our next step in terms of when we have these complicated systems and we're doing force analysis on them, we have now thrown in our ability to study the net torques present on an object or a system. Okay? The next thing we're going to take a look at in the next little mini set of videos is rolling, which is a very, very interesting topic and one that we haven't touched yet. So I'll see you later for those videos.